Oh, hi, everybody. I'm going to talk briefly today about assigning formal charge and showing when you have a polar or covalent bond. As you know from general chemistry, ions and even molecules can carry electrical charge. You can have cations carry a positive charge. You can have anions or atoms carry a negative charge. Essentially, this is a bookkeeping method. And what you end up doing is you compare the number of electrons around a given atom with the number of electrons around that atom when it's neutral. Um, if the number of electrons around the atom is the same as the number of electrons around the atom when it's neutral, then the atom is neutral. It carries no electrical charge. However, if you have more or less electrons around the atom, than you would expect for the neutral atom, you will have negative and positive charges associated with the atom. Rather than explaining this verbally, I think it's much easier if I can show you how to do this. Okay. So we're going to use the circle method. So we're going to draw the circle around the atom of interest, bisecting, cutting in half any chemical bonds to the atom. And within the circle, we will include all non-bonded electrons. So let me show you. And then, well, let me show you. So here's a species. All the bonds to the oxygen and all the lone pairs on the oxygen are shown. So what we do is we do this. We draw a circle around the atom that we're focused on. And we are bisecting, right? We are bisecting the bond to the atom. There's only one bond to the atom. If there are two, we would bisect both bonds. The lone pairs of electrons are enclosed in the circle. Okay. Then what we do is we take the number of electrons in the neutral atom. It's an oxygen. Oxygen is in group 6A, so it has 6 valence electrons. We subtract all the non-bonded electrons, the lone pairs. There are 3 non-bonded pairs of electrons, or 6, right? You have 2, 4, 6. And then you subtract 1/2 of the shared electrons. So we have 1 bond to the oxygen that corresponds to 2 shared electrons. You subtract half of that, or 1. You subtract 1. If you just subtract the number of bonds to the atom, that's the same thing. There's 1 bond to the atom, so you subtract 1. So we have 6 neutral and 6 electrons in neutral oxygen. There are 6 lone pairs and non-bonded electrons, and we have 1 bond to oxygen. So 6 minus 6 minus 1 is -1. So there is a -1 charge associated with that atom. Remember, neutral oxygen had 2 bonds and 2 lone pairs. Talked about that yesterday. You can see when oxygen carries an electrical charge, -1, the bonding rule is different. It only forms 1 bond with 3 lone pairs associated with it. So let's look at the next one. So here I'm going to show you several examples. Okay, so we already did this. We have an oxygen with 1 bond and 3 lone pairs. So I'm going to do this again. We draw a circle around the atom, enclosing the lone pairs and bisecting the bond. We have 6 valence electrons on a neutral atom. We have 6 non-bonded electrons, and we have 1 bond. We have 6 minus 6 minus 1 is -1. You see this, this oxygen, of course, as on the previous slide, carries a -1 charge. Right? So let's take a look at a different example. Let's look at the middle one. So we draw the circle around the oxygen, bisecting the bonds to the oxygen, enclosing the lone pair within the circle. Okay. We have 6 valence electrons in a neutral oxygen. That's the same. Have 3 bonds. So we now have 6 minus 2 minus 3, that's plus 1. So the charge on this oxygen is positive 1. The oxygen has a positive charge on it, okay? Just gave away the next one, but let's work through it. So you see the bonding rule for positive oxygen is 3 bonds and 1 lone pair. We saw here negative oxygen, the rule is 1 bond and 3 lone pairs. For positive oxygen, the rule is 3 bonds and 1 lone pair. Okay, let's do the last one. So in this case, we are going to draw a circle around the carbon. Carbon has 4 valence electrons in neutral carbon. It's in group 4A. There are no non-bonded electrons, because in these problems, all lone pairs, if any, are shown. And there are 3 bonds to the carbon, so minus 3 bonds. So we have 4 minus 0 minus 3, that's plus 1. So the charge on this carbon is positive 1. You see a positive carbon contains 3 bonds and no lone pairs. Now you might ask, this carbon only has 6 valence electrons around it, right? The 3 bonds. It doesn't have an octet. Is that right? And the answer is yes. We can have species that do not have an octet. It turns out they're just very unstable species. And this carbon with a positive charge is just a highly reactive and unstable species. Let's go to the next slide. So let's reverse this now. And let's show structures where we show molecules where the formal charges are shown, and we'll try to calculate the number of non-bonded electrons. Okay, so let's start over here with the nitrogen species. You draw the circle around here, right? So neutral nitrogen has 5 valence electrons. It's in group 5A. It has X minus X non-bonded electrons. We don't know, because in this problem, the formal charge is shown, and we have to calculate the number of lone pairs. And then we have 4 bonds. So what we have is 5 minus 4 is plus 1, minus X equals plus 1, which is the charge on the nitrogen. So you see X equals 0. So a positive nitrogen has 4 bonds and no lone pairs, which makes sense. The 4 bonds corresponds to an octet. Okay, let's try the bromide ion. I'll redraw it, Br minus. So in these problems, we're showing the formal charge, and we're trying to calculate the lone pairs. In the previous slide, we showed the ion with A, so it has 7 valence electrons. There are no bonds to it, right? And we're calculating the number of lone pairs, non-bonded electrons, which we'll call X. We don't know what that is. So if 7 minus 0 is 7, minus X equals minus 1. So a bromine ion has 4 lone pairs around it, okay? So in that way, you can either calculate the formal charge on an adenine if you're giving the structure and you have to show the number of lone pairs, or you can calculate the lone pairs if you're given the structure and the formal charge on the atom.